Hello friends, welcome to lecture number 2 of integral transforms, and this is my Insta ID ozalekejit123. So today we're going to discuss about Fourier sine and cosine integrals. So in the last lecture, in the lecture number 1, which is in which we have discussed about Fourier integral formula, Fourier integral theorem, right? And link of the last lecture, that is link of the first lecture, lecture number 1, is given in the description box. If you haven't watched yet, then please go through, okay, for better understanding. And before we start, please subscribe the channel if you are new to my channel. Also share with your friends, support me to grow my channel, inspire me to create new contents for you. Now let us discuss about Fourier sine and cosine integrals, right? So let's start.
As in the last lecture, we have discussed that Fourier integral theorem. According to this theorem, we have got that f of x given by 1 by pi double integration 1 from 0 to infinity, then minus infinity to plus infinity, f of t cos u into t minus x du dt. We have got it, right? So now you see, depending on this function type, what kind of function is this? So it is odd or even, okay? Depending on f of t, this is odd or it may be even, right? So it can be written, this can be written in two different forms. One is, Fourier sine integral form, Fourier sine integral form. If this function f of t is odd, then it can be written in Fourier sine integral form, and that is given by f of x 2 by pi double integration from 0 to infinity, then again 0 to infinity, f of t sine ux du, then sine ut dt. That's what we're going to have. And if it is even, then the given function f of x, then it can be expressed in that can be expressed in Fourier cosine integral form, Fourier cosine integral form, Fourier cosine integral form, that is f of x is equal to 2 by pi double integration from 0 to infinity, then again from 0 to infinity, f of t cos ux du, then cos ut dt. That's what we can have, right? So now let us prove one by one, okay? So now let us discuss about Fourier sine integral. So according to Fourier sine integral transform, we have f of x 2 by pi double integration from 0 to infinity, and then again from 0 to infinity, f of t sine ut sine ux du dt, and that's what we have got. So let us prove this. So again we're going to use the Fourier sine integral Fourier integral theorem. So Fourier integral formula is this. So this is the Fourier integral formula, right? So let me write that. So this is the Fourier integral formula, right? So now let us expand cos ut minus x using cos a minus b formula. Then what we're going to have? So then we can have cos ut cos ux plus sine ut sine ux du dt. That's what we're going to have, right? So this is nothing but cos a cos b sine a sine b, right? So that's what we're going to have. So then we can split it this way into two terms, right? In this way, So let it be equation number 1. So now you see, as I have already told you that here this f of t must be odd. Right, it must be odd. So when f of t is odd, then the f of t into cos ut is also odd, because you see here, you see cos ut, this is even function, and f of t is odd function, right? So in that case, suppose we have two odd functions. One is f of x, this is odd. If this is odd, then f of minus x is minus f of x. Then we have an even function, suppose p of x. If p of x is even, this is odd, this first one is odd and this is even, then p of minus x, that's going to be also p of minus x. But if you take their product, then what you're going to have, f of minus x, sorry, here you see we have taken p of x is even, that's why p of minus x, that's going to be p of x. And if you take the product, f of minus x into p of minus x, then you're going to have minus f of x, p of x. So here you see, as this product is minus f of x and p of minus f of x into p of x, that's why it is odd, right? So to be even, this must be positive, right? So similarly, when you're going to have both the odd function, if this is odd, then p of minus x is going to be equal to minus p of x. In that case, this product going to be positive and this is going to be even in that case, right? So hope you have understood this. So now let me cut it. So as this is even, this is odd, so the product is also odd. And for odd function f of x, suppose we have an odd function, then minus integration from minus a to plus a f of x dx, that's going to be equal to 0, and hence we can write minus infinity to plus infinity f of t cos ut cos ux du dt is equal to 0. Actually here you see this part, f of t cos ut integration minus infinity to plus infinity f of t ut dt, that's going to be equal to 0. If that is the case, so we can write double integration from 0 to infinity, then minus infinity to plus infinity, this whole part is equal to 0, right? This whole result gonna be equal to 0, right? So now you see but f of t sine ut, that is even, right? Because you see this is odd, this sine function is also odd. If we have both of them odd function, then their product gonna be give you the product gonna be even function. As I have already explained, that if you have minus f of x is equal to minus f of f of x, f of minus x is equal to minus f of x, for f of x is odd, right? When you have another function that is p of minus x, that's gonna be if p of x is also odd, f of x is also odd, right? In that case, f of minus x is minus f of x, p of minus x is minus p of x, and if you take their products, then that's going to be positive f of x, p of x. So that means product of f of x px is even, right? So that's how we get f of t sine ut, that is even. And for even function we have this condition that integration from minus a to plus a, if f of x is even, if you assume f of x as an even function, then integration from minus a to plus a of the even function f of x dx, that's going to be 0 to a integration from 0 to a f of x dx. So if we apply this here, so minus infinity to plus infinity, instead of this we're gonna write 2 into 0 to infinity, right? That's what we're gonna do here. So hope you have understood this. So in that case, the equation number 1 becomes this, and this is the sine integral, which is proved, right? So hope you have understood this. Now let us discuss about the cos integral. Okay, let me go to the next slide. Fourier cosine integral. So Fourier cosine integral, that is given by this f of x 2 by pi double integration from 0 to infinity and minus infinity to plus infinity f of t cos ut cos ux du dt, right? So in this case, this f of t must be even, right? So now let us prove. Again, we're going to proceed same way as we did in Fourier sine integral. So from up to equation number 1, we're going to follow the same steps. So let me write faster. So this is the Fourier integral formula. So applying cos a cos b, cos a minus b formula, we are going to have this, and which gives you this result, splitting this. This is equation number 1. So let it be equation number 1. That is how we have got the equation number 1. So here f of t is even. So if it is even, then f of t, cos, here we have taken f of t is even, right? And sine ut is odd function. We know that sine is odd function, as I have already told you that if this f of x is even, and suppose p of x, another function that is odd, suppose, in that case f of minus x, that's going to be f of x, because this is even function, then p of minus x, as it is odd function, minus p of x, we're going to get this. So their product is again minus f of x into p of x. So as we are getting here minus, so that's why product of even and odd function is odd, right? So hope you have understood these things. So now this part is odd, this is odd function, is odd function, as sine ut is odd function. And for odd function, suppose we have a odd function f of x, then from integration from minus a to plus a f of x dx, that's going to be equal to 0. So if that is the case, then this whole part going to be equal to 0, because you see integration from infinity to f of t sine ut sine ux dx du dt. So let me write here one more integral, 0 to infinity. Here you see actually minus infinity to plus infinity f of t sine ut dt, that's part going to be equal to 0. If that part is 0, then this whole part is going to be equal to 0, right? So here let me tell you one more thing, just wait. So but f of t cos ut, that's going to be even function here in this case, because f of t we have considered even, and cos ut is also even, so both even, so their product going to be even. And for even function f of x, suppose f of x is an even function, then integration from minus a to plus a f of x dx, this can be written 2 into 0 to a, instead of infinity, 0 to a f of x dx. So if we apply that here, then this equation number 1 becomes this. So we're gonna get this. So this is the cos integral transform, right? Hence proved. So hope you have understood this.
Now let us solve a problem here. The question is using Fourier sine integral so that this integral is equal to pi by 2 e to the power minus kx. Okay, so let us solve this. First let me write the given what is given here, what we need to show. This is it. So that is what we need to show, right? So in this case here you see this e to the power x, e to the power minus kx, this term e to the power minus kx, that should be taken as a function of x, f of x. This function of x is taken as f of x, and hence we will consider f of t. So replace the x by t, then e to the power minus kt, right? So now you see, as we are to apply here sine integral theorem, sine integral, Fourier sine integral, so which is nothing but this one. So this is the Fourier sine integral, right? So let me write within the box, just do it, give me a second. Okay, so here you see this is the Fourier sine integral, right? Fourier sine integral, right? So here we have u and du dt, this is u t, but instead of u, instead of du, we have here d lambda. So that's why we're gonna use lambda instead of u, right? So using the Fourier sine integral, we're gonna get this, right? This is the Fourier sine integral. So let me write in terms of delta, just wait. So here instead of u, we're gonna put lambda. Okay, so let me write here, just wait. So here it is lambda, so this is lambda x d lambda, so it is also lambda, here also lambda, lambda and lambda. So here you see this is according to Fourier sine integral, f of x is equal to this one, and f of x we have considered this, right? So which is written here instead of f of x, right? And here you see, and instead of u, here let me just clean this part. So instead of u, we have put here lambda. Okay, so hope you have understood this. Now here I have separated this term like this. Okay, so what we have done here, I have written the functions of t, which are the functions of t with dt separately, like this way, and here it is function of lambda. Okay, so hope you have understood this. So now let us evaluate this integral. Okay, 0 to infinity, integration from 0 to infinity e to the power minus kt sine lambda t dt. Okay, so first let us take the integral only without limits. Okay, so dt. So here we're going to use the product rule. What is the product rule? So integration u b dx, that is equal to this u is the first function and b is the second function, right? So first function, integration of second function, minus integration derivative of first function, then again integration of second function dx all dx, right? So we're going to use it. So how to choose the first and second function here? So we're going to use this order I let. So trigonometric functions comes before the exponential function. That's why we're going to consider sine lambda as u, that is the first function, and exponential function should be taken as the second function, right? So hope you have understood this. So let me clean these things. Just wait. Okay, so now, so let me rearrange it. So that's what we have got. Okay, now apply the product rule, and doing so, what we have got this step, right? So here you see, just let me explain it. Just wait. Here you see, so what we have done here, so this is the first function, that is u, and integration of v dt, then derivative of u here, derivative of sine lambda t. And so how we have got this, if you see, this is nothing but u dash. U dash means u is here we have considered u as sine lambda t. U dash means derivative of, if you differentiate it with respect to t, sine lambda t, then it's gonna be equal to lambda into cos lambda t, right? Cos lambda t, because you have already got that ddx of sine mx is equal to m cos mx. You have got this, so we have applied that one. So hope you have understood this. So now let us simplify this. So what we can do here, just what we have got, so this is equal to now sine lambda t and integration of this e to the power minus kt. So we know integration of e to the power mx dx, this is equal to e to the power mx by m. If you apply that, then instead of m we have minus k, so here will be also it will be also minus k. So that's why what we're gonna have, so we're gonna get this e to the power minus kt by minus k, then minus, just wait, minus, so lambda is constant, that can be taken out. So in the next step we're going to take that lambda out. Okay, then again if you integrate this term as well, again you're going to get the same result, e to the power minus kt by minus k, right, dt. Then so let me write here. So here you see here this minus and minus gives plus, so that's why plus, and lambda is taken out and k is also taken out. These two are constants, so both are taken out here. So then integration cos lambda t into e to the power minus kt dt by here k, k is taken out. So on the left hand side we have got this, right? So this is the integration of this part. So now here you see, if we apply the u into v rule here again, then what we're gonna get. So let me copy this and let me go to a new slide. Okay, so then what we're gonna have here, so this is the last step we had here. Again we're gonna apply the u into v rule. So in the second part, just wait, so here if we apply here u into v rule again, that integration of product of two function u into v dx, if we apply that, then we're going to get this result, right? Here you see, that's what we're going to have. Just wait, so here we should get a lambda here. Okay, and derivative of, here you see derivative of this cos lambda, sorry, ddt of cos lambda t. Actually we should differentiate with respect to t, not lambda. So in the previous slide I have shown, I think with respect to lambda, so forget about that. So it should be lambda minus sine lambda t, and that minus lambda sine lambda t, right? That should be the result. That's why we have got this one. So hope you have understood this. So now simplifying this, what we have got, so this is minus, this is minus, this is minus, odd number of negative signs, so remains negative. Then we have got this one, right? Just wait. So if you multiply this one with this lambda by k, then we're gonna get lambda square by k square, right? That's what we have got. So we have got this. Now let me write the left hand side. Now what we're gonna get, let us bring this to left side. So then what we will get, this is the left hand side now, and on the right hand side what we're gonna have this, right? This is the right hand side. So hope you have understood this. Now you see, so here we're gonna get this term, we're gonna take this term common, integration of this and this. On taking these two common, we have got 1 plus lambda square by k square, then integration of this, right? So on the right hand side we can take this part common, right? So then what we're going to have, e to the power minus kt is taken common now, and e to the power minus kt by k square is taken common. Then what we're going to have, we're going to have this. Let me write here, just wait. Here this part is taken common, right? So this is taken common. Okay, so we're gonna get this result, right? So now what we can do, so if you take LCM here, it's gonna be k square plus lambda square by k square, and multiply both sides by k square plus lambda square, and on the right hand side as well, k square by k square plus lambda square. And doing so, what we can have, we're gonna get this, result, right? So here e to the power minus kt, that's what we're gonna have, right? So then, right, this is the result we're gonna have. So here this k square is gone, this two cancels. Then what we can have, so this is what we have got, the integration. We have evaluated the integration. But here you see, let me go back to the previous slide. Here you see what we need here we need the value of this, right? So we need integration of this from 0 to infinity, we need that. So let us evaluate that value. Okay, so we have got the integration, we have evaluated this integration from integration minus kt sine lambda t dt. We have evaluated this. Now we need to evaluate if the lower limit is 0 and the upper limit is alpha. Then let me go to the, so here you see this is the evaluation of the integral. So now as we need the integration from the integration of this from 0 to infinity, so we're going to put the upper and lower limit 0 to infinity. Let us copy this and let me go to the next slide. Okay, so let me write the last step again, what we have got. So this is the last step that we have got, just wait. So now we know e to the power minus infinity is 0, e to the power 0 is 1. So here if you put this alpha here, then it's gonna be e to the power minus k into alpha t, means e to the power minus alpha, you can consider that. So that's gonna be equal to 0. So for upper limit, this whole thing is 0 because whole thing is multiplied by this function, right? So that's why we have got 0 here. Then minus, let's put 0 now. Let's put 0. On putting 0 here, e to the power 0, that's going to be 1. Then if you put 0 here and here, sine 0 is 0 and cos 0 is 1. So in that case, so this is going to be we're going to get this result, right? sine 0 is 0, cos 0 is 1. So putting this, we're gonna get this result. So now that's why we have got finally the value of this part, right? This is suppose equation number 1. So now let me go back to the first slide. Here is the first slide. Now let me copy this equation. This function is equal to this, right? So now let me copy this equation number 1. Now let me go to the last slide. Here is the last slide. Now let me write the equation number 1. This is the equation number 1. Okay, let me rearrange it. Okay, now you see, using this equation number 2 in 1, so we're gonna get this result, right? So here, we can replace this part by this value, right? And doing so, we have got this result, right? Now if you simplify this, what we're gonna have, we're gonna get this result, right? So that's what we needed to prove. So hope you have understood this. Okay, so in the next lecture, we're gonna discuss about the complex integral of Fourier integral, or complex form of a Fourier integral. We're gonna discuss in the next part. Okay, so stay connected. See you in the next video. Thank you for watching.